Okay, all right. So a very good evening to one and all, and let us start today's session. Today's session number is 8, and in today's session we are going to see the reactive power compensation in distribution system. In the last section, in the last session, we have seen the backward forward load shift algorithm for distribution system. Now in today's system, we are going to see reactive power compensation in distribution system. So first, anyone can verify that are you able to see the screen?
Yes, sir. We can see.
Okay, I think today Ramesh is present after a long time.
Yes, sir. Thank you.
Why were you not attending the session?
Uh, Actually, sir, I am out of city due to some company work. That's why I am unable to attend.
Okay, no problem. So let us start. So first, we will see this shunt capacitor for power factor corrections, where we will see the concept we learned in undergrad course, like power triangle, how this with the help of this power triangle we can easily analyze this power factor, and we can find the power factor, and we can solve the problems based on this power factor correction. So at the load end, what is done? The capacitor is connected so that reactive power component Q of the load can be reduced or totally suppressed. Assume that here load is supplied with real power P1 and lagging reactive power Q1 and apparent power S1 at a lagging power factor of cos theta 1. So from this power and from this power given, we can make this power triangle where this on x-axis we have P1, and then perpendicular to it we have reactive power Q1, and this theta 1 is the power factor angle. So the relation you can write for power factor is cos theta 1 P1 upon S1 equal to P1 under root P1 square plus Q1 square. Now what you have done for power factor correction, either you minimize the or either you minimize the reactive power component that is flowing from the distribution substation, or you can totally suppress by providing the reactive power locally. The concept is that we are not taking the reactive power from the far end, we are taking from the local, means at the node, at the buses we put this capacitor, shunt capacitor, and that provide the reactive power locally. We are not taking the reactive power coming from the substation, and at the substation it is coming from the generation end. So there is a higher power losses if you demand reactive power from the substation. So here we have installed shunt capacitor at the load end, and you can see this how this power factor is improved from cos theta 1 and to cos theta 2. So you are minimizing the power factor angle. If you are minimizing the power factor angle, that means this power factor also improves. So this is the reactive power that is being supplied by the capacitor. So if you see the reactive power that is being supplied by the capacitor, then the net reactive power component that is coming from the substation is Q1 minus QC, Q2. So this reactive power demand from the substation is reduced. If you want to make the unity power factor of the feeder, then whatever the load demand, you should supply all the load demand from the capacitor. And suppose if you have to make this reactive power unity for the feeder, then theta 1 should be reduced to 0. In this case, we have taken that theta 1 reduced to theta 2. This concept will be more clear when we will solve the problem based on this power factor correction. And here one of the examples shown on the power factor correction, where we have assumed 100 kVA load, 100 kVA apparent power. This is apparent power given with power factor 0.8 lagging, and we would like to correct the power factor to 0.95 lagging. What would be the capacitor size? So since apparent power is given and power factor is given, then you can find the active power and reactive power. So active power is S cos phi and reactive power is S sin phi. So cos phi power factor is given 0.8, therefore sin phi is 0.6, therefore phi 36.9 degree. Therefore this active power is 80 kilowatt and reactive power is 60 kVAr. Now the desired power factor is 0.95. So let us calculate this power factor, desired power factor angle, that is cos inverse 0.95, that comes as 18.2 degree. Therefore this if you here you have to find the reactive power capacitor size. So you can use this power factor triangle where you can substitute tan 18.2 degree, because you note this desired power factor angle 18.2 degree. So tan tan of some angle is perpendicular upon base. So perpendicular is 60 minus QC and base is 80. So therefore this capacitor size comes out at 33.7 kVAr. Now if you refer the Turan-Guren book, there you can see the significance of reactive power compensation. So in this case, you see that what is the effect of reactive power on power factor. So whatever the apparent power in the first figure, whatever the apparent power, that is equal to the reactive power, is equal to the active power or real power. So in that case, your power factor comes out to be unity or 1. And the second case, we have, so in this example, we have put active power demand for the load is fixed, and we are varying we are increasing the reactive power, and we will see what its impact on power factor. Now we have the reactive power for the load is increased, and it is 48.43 kVAr. You can see this power factor is reduced, and again in this case, in the middle case, we have increased the reactive power 75 kVAr and active power as it is. So power factor again reduced to 0.8. And in the fourth case, we have increased the reactive power to 102 kVAr. So again, if this active power demand for the load is increased, then this power factor again deteriorates. So this power factor comes out to 0.7. In the last case, we have increased this reactive power equal to 133.33 kVAr. So in this case, again, it is reducing, this power factor is reducing. So power factor comes out to be 0.60. So we can see that this reactive power demand increases with reduction of power factor. And in the second case, we have considered the apparent power equal, and we are seeing the variation of reactive power and power factor. So in the last case, we have fixed the active power, and this reactive power is increasing and this power factor reduced. Now in the second case, we have fixed the apparent power, and with the increase of reactive power, this power factor deteriorates. So if with the power factor of 0.90, this reactive power is 43.59 kVAR for the same apparent power. And with the reactive power of 60 kVAR, this power factor comes out as 0.80, and with the reactive power of 71.41 kVAR, this power factor comes out as 0.70, and with the reactive power of 180 kVAR, this power factor comes out as 0.60 kVAR. So you can also say that with the increase of with the decreasing of real power, the power factor is also reducing, but the reactive power will increase with the reduction of power factor. So apparent power is fixed, this active power is reducing, and this reactive power is increasing with the reduction in power factor. Now let us see this concept of leading and lagging power factors. That is very important. Many of you have confusion regarding that when you have to consider the lagging reactive power or leading reactive power. So we will see for both the loads and generators. So the concept of lagging and leading reactive power factors depends on the direction of flow of reactive power. And for load, the power factor is lagging. That means your load is inductive, and this convention is Q is greater than 0. If Q is greater than 0, and that means load is consuming reactive power. And the fundamental and the principle behind load is that the principle of load is that it consumes. So something is positive for load, that means it consumes that thing. So here Q is greater than 0, that means load consumes reactive power. And if nothing is written, then you have by default you should assume that it is lagging reactive power. Therefore, this load consumes lagging reactive power. And opposite of lagging, this will be leading. So, you can also say that load supply leading reactive power. If anyone is saying that load consuming lagging reactive power, so in contrary, you can also say that load supply leading reactive power. Now, if Q is less than 0, that means power factor is leading, and we denote capacitive load. And for capacitive load, Q is less than 0. Like for capacitor, Q comes out as negative. And for inductors, this Q comes out as positive. If Q is negative, and the principle of load is that if something is negative for load, then it should supply. So Q is negative, that means load supply reactive power. And its supply reactive power means you can also say that it supply lagging reactive power. And in contrary, if load is supplies lagging reactive power, then it means that load consumes leading reactive power. So here you can understood from the table also. Here I have considered for generator and load both. So in the last slide we have shown for load. In this session, in this tutorial session, the most we have to relate with the load only. But for better understanding, I have taken considered generator also. So for load, sign convention is positive if it consumes real or reactive power, and, vice versa for generator. For the generator, it is same. If sign convention is positive, that means it supplies real reactive power. So the principle of load is that it should consume. That's why if sign is positive, that means load is consuming real reactive power, and the fundamental or principle for generator is that it should supply. And if sign is positive, that means generator is supplying real reactive power. And from this table, you can see that for generator is Q is positive, that means supply reactive power. And you can also say that supply lagging reactive power, and vice versa. In other words, you can also say that it consumes leading reactive power. And if Q is negative, that means it consumes reactive power. And you can also say that it consumes lagging reactive power. And you can also say that it supply leading reactive power. And for load, you can say that if Q is positive, that means it consumes reactive power. And you can also say that it consumes lagging reactive power. And in other words, you can also say that for leading reactive power, it supply leading reactive power. And if Q is negative, it supplied reactive power. You can also say it supply lagging reactive power. And in other words, you can say that it consumes leading reactive power. So this is all for in summary about power factor triangle and this concept of leading and lagging reactive power. Still here any doubt? If you have any doubt, you can ask. Otherwise, we can move to the next section. Okay. Now let us see the placement of capacitor bank in the on the feeders, and what should be the size, what should be the optimal size, what should be the optimal placement, and what should be the optimal size for the capacitor bank in the distribution system. So for this, we have to know some expression, like here this lambda. We should know the lambda. So lambda is the ratio of reactive current at the end of line segment upon reactive current at the beginning of line segment. So if the load is uniformly distributed across the feeder, then this I2 will be 0, and you can say that's lambda equal to 0. And if the load is lumped or concentrated, that means I2 equal to I1, and this makes lambda equal to 1. So for uniformly distributed load, lambda will come as 0. And for lumped load or concentrated load, this lambda comes as 1. And then another term, alpha. Alpha is the reciprocal of 1 plus lambda square. So you should know this alpha term also. And now the degree of capacitive compensation, that is C. So C is defined as IC upon I1. So it denotes the capacitor size, means the degree of capacitive compensation. So C the ratio of kVA of capacitor installed upon total reactive load. So C is IC upon I1, that is kVA of capacitor installed upon total reactive load. Now for a single capacitor bank placement across the feeder, sorry. So this expression is very important. Delta PLS 3 alpha C x1 into 2 minus x1 plus lambda x1 minus C. So for single capacitor bank placement, the per unit power loss reduction expression is this one, 3 alpha C x1 into 2 minus x1 plus lambda x1 minus C. So this expression is very important and you need to remember. because in the problems and the exam or in the assignment, many problems are based on this single capacitor bank placement, and no question being asked on this double capacitor bank placement
Noted, sir.
or n capacitor bank placement. So you are familiar with this alpha term. So alpha is the reciprocal of 1 plus lambda square, and c is the degree of reactive compensation, and x1 is the per unit distance of the capacitor bank location from the beginning of feeder segment. So here I will just give you hint for this current assignment. For the first problem, you have to use this expression.
Can you go to previous slide, sir? Degree of compensation. Can you explain?
Yes. Degree of capacity in the question it will be specified what amount of compensation you want to use from the capacitors, like third, fourth.
Okay, sir. Okay. You have to remember this uniformly distributed I2 is equal to 0.
This expression is similar.
Previous.
Is this expression is true for both informally distributed load or lumped or concentrated load. For lumped load, this alpha and this alpha value will change.
Yes. Yes. Okay. Yes.
Like if you I will show an example. Like if for a feeder with uniformly distributed load, like the feeder is given with uniformly distributed load. Uniformly distributed and a fixed capacitor bank rated at 2/3 of the total reactive load. So this is defined by C. So it is given that a fixed capacitor bank rated at 2/3 of the total reactive load. So C is defined from this statement. So informally distributed, first thing is given informally distributed load. So from the informally distributed load, what you can get. So
Lambda is
informally,
equal to
yes, correct, Ramesh. So I2 equal
and
to 0, I2
and
equal to
lambda.
0, and we know that lambda equal to I2 upon I1. So this lambda will become 0.
Lambda. What is the lambda equation, sir? I2 by I1.
Yes, lambda is I2 upon I. I2 is the current at the end of segment, and I1 is the current at the beginning of the segment. Reactive current at the end of line segment, I2 is the reactive current at the end of line segment, and I1 is the reactive current at the beginning of line segment. And if the problem specified that you are installing fixed capacitor bank rated at 2/3 of total reactive load. So here, if they specified that a fixed capacitor bank you are using and is rated at 2/3 of total reactive load. So this means that C is given, the degree of reactive compensation, and C comes out as 2/3. and in the third part they will specify the location, and this capacitor is located at bank is located at 2/3 of distance distance on the feeder from the source. So this will denote x1. So x1 is 2/3. So in problem they will tell another location also, another degree of reactive compensation also. So you can vary these two things and you can get power loss reduction. So I have taken this example on optimal location, optimal size, and this location and size may will vary. So the power loss reduction, if you put all this value, so from lambda also you can find alpha. So alpha equal to 1 plus lambda square. So alpha will come as 1. So 3 into alpha is 1, C is 2/3, and x1 is 2/3, and 2 minus x1. So x1 is 2/3 plus lambda x1. So lambda x1 is 0 minus C is 2/3. If you want to get in percentage, so multiplied with 100%. So you will get 4/3 into inside term is 2/3 into 100. So you will get 88.889%. So approximately equal to 89%. So this example we have considered optimal size and optimal location. But now if you suppose this capacitor bank compensation, this reactive power compensation is changed. Now in the I think in your problem they have tell you to take C as third by fourth and x1 is third fourth. So this delta PLS will be changed. And can anyone tell if this capacitor size and location is vary from these two? Will delta PLS will increase or decrease? I am asking that if your capacitor bank, if your degree of this compensation, reactive compensation, or this location of capacitor bank is changed from these two values, what will the effect on power loss reduction? Will it increase? Will it be more than 89% or will it be less than 89%?
Voltage will be vary. Voltage drop will vary. Then what
I'm
will
asking that power loss will be increased or decreased from 89%. Increase or decrease? Only you have two options.
if we distance move or
Increase.
Yes.
It will be increased.
Any other one? Why it will increase? So I will
Uh,
first show. Yes.
if the capacitor bank location is increased, then power loss will be increased because it's directly proportional to each other.
You can no. You let us see for this slide and then we will come. So this you can refer to the class lecture where sir has derived this optimal power loss reduction expression, and from this optimal power loss reduction expression, and this expression is for single capacitor bank placement. And if you want to write the general term, like this expression comes from, so this expression is not important. This expression comes from this delta PLS 3 alpha C 1 minus lambda C minus C n square plus C square n 4n square minus 1 upon 12. So from this expression, if you substitute n equal to 1 for single capacitor bank placement, you will get the optimal power loss reduction expression 3 alpha 1 minus lambda into C minus C square plus CQ upon 4. Yes. So now if you differentiate with respect to C and equal to 0, then you will get the optimal value of C, and the location is this one, 2/3 1 minus lambda. And therefore this power loss reduction expression will come out as 3 alpha upon 1 minus lambda into 8 upon 27. So if you substitute C equal to 2/3 in this expression, like, then this C minus C square plus CQ upon 4. If we substitute 2/3, then 2/3 minus 4 upon 9, and it is CQ. So 8 upon 27 into 24. So what value it is coming? It is 7/108.
0.145.
Yes.
0.145.
I think in this something is wrong. X1 is 2/3. So, but not coming 8 upon, it is coming 4 upon 27. 4 upon 27. Three. So you'll just check. But for here, I want to say that for lambda equal to 0, that is uniformly distributed load, this power loss reduction will be 8 upon 9 per unit, or capacitor placed is 2 upon 3rd per unit distance with C equal to 2/3 per unit size. So this is barely 2/3 thumb rule for capacitor placement. So for uniformly distributed load, your capacitor size should be 2/3 and the location should be 2/3, so that you will get the optimal power loss reduction. And if you vary these values from these two values, your power loss should be reduced. So it should be reduced from 9%. Now, if you have used some location that is different from 2/3 per unit, like you assume 4/3 per unit, and if you also consider capacitor size different, then your power loss reduction should be less. But for ideal, but for this optimal, but for this optimal case, where we have considered this 2/3 thumb rule, where this capacitor placement is 2/3 per 2/3 per unit distance and capacitor size is 2/3 per unit, then you have this power loss reduction is 8 upon 9 per unit. That is 89%, approximately 89%. So Ramesh, you are telling that it should increase, but if you take something different from these two values, x1 equal to 2/3 per unit and c equal to 2/3 per unit, then power loss should be power load should be decreased. Power loss reduction should be decreased. So be careful with this term. It is saying power loss reduction, how much percentage reduced. So if you have considered different values from the optimal case, then power loss reduction should be reduced. So in this
Okay.
case only maximum power loss is reduction is happening. So if you consider these two values, in that case maximum power loss reduction is happening. Another case it should be reduction is happening less. Power loss reduction is happening less.
Correct. This is the calculation base actually.
Y- Yeah, you can refer to this lecture number, that is last part of Big 8.
Okay. Actually, I have not seen the lecture. It's pending from my. I will once see
Yes,
lecture.
go through the lecture.
Yes, yes. I have one more doubt. Can you elaborate about the PU units per units PU per units? How to consider?
For distance, you can see like if your feeder length is 4 kilometer, so your distance is 2/3 of 4 kilometer, like that. But for capacitor size, it should be the what amount of load reactive power, what is the amount of reactive power demand from the load, like this total reactive load, and what means like your reactive load is 8 kVAR. Reactive power demand from the load is 8 kVAR, and C that comes out as 2/3 of 8 kVAR. So it is coming as how much? So
Around 5.
so first you convert this 8 kVAR into apparent power, like suppose 10 kV is given. So it is coming as 0.8. Here kVA upon total active load. I have to check means how this per unit is defining here. But for the problem, they will directly give you in the they will directly define this degree of compensation 2/3 or, and that you have to put in the expression, and this expression C equal to 2/3 alpha means or x1 is equal to 2/3. These are means for the expression these are values given in per unit. And for this numerical type, how we will find that I have to check.
Okay, sir. Okay, thank you.
Let us begin with this first problem. So the problem is that which of the following is are correct about reactive power compensation.
D. Answer D.
Yes, you can type on the chat box also. So today we have more attendance. I think 1, 2, 3, 4, 5, 6 people are present. Here it is asking about means not correct about the reactive power compensation. So what are the advantage of reactive power compensation? First is reduction of power loss. It is advantage. Improvement of bus voltage profile. Yes, it is also advantage of reactive power compensation. Another is power factor correction. It is also advantage. Increase in ampacity limit of line. No, it is not correct.
No, no, sir. When we do the reactive power compensation, yeah,
Yeah.
the current drawn from the source will be reduced, so the ampacity limit will be increased automatically because the capacitor,
Yeah.
the compensation for reactive power compensation will be supplying the current, so that the current drawn from the source will be less. So that means ampacity limit will be increased.
Yes.
When we calculate the power factor compensation, we can see that when we add a capacitor, the current drawn from the source will be reduced considerably. That means the ampacity limit of the line is increased.
Yes, your point is also correct. Which of the following are not correct about the reactive power compensation? Region appears. So now power loss is correct. Improvement of bus voltage power factor correction is also correct. Reduce the impulse in between. No, this question is dropped or what? Because you are not correct about reactive power compensation. Increase in capacity limit of line. Okay. I think uh,
This is
I
the
am
previous
also,
questions. Previous questions.
yes, previous question.
But
I
in
also got
the present
confused.
present assignment, we have a similar question.
Yeah.
But
So
in that one, the one is increase the voltage drop between sending and source. So that is okay. Increase the voltage drop between
no,
sending.
no. Means like why they are giving this means first why are they giving this answer D as correct? Because this is the internal characteristics of line, not the due to reactive power compensation. Reactive power compensation, what does it lead to? It leads to that less current flowing from the line, but it is not changing the limit, means current limit of the line. That's why this answer is incorrect. It just
Yeah, got it,
sorry.
got it, got it.
So D option is correct. Everyone got this point or not? Because if you are doing reactive power compensation, this power apparent power demand, apparent power apparent power coming from the feeder is less. You are providing reactive power locally, and that leads to lesser current. So it does not mean that it is increasing the ampacity or reducing the ampacity of limit of line. It means that because this ampacity limit of line is the internal characteristic of line, not due to this reactive power compensation. When you are selecting the line, you are defining its limit. What should be the maximum current that allow through it? So D option is correct. So let us come to the next problem. A power system has a 8000 kVA capacity and is operating at a power factor of 0.7 lagging, and the cost of synchronous capacitor is $15 per kVAR. Find the investment required to correct the power factor to unit power factor. Yes, Div, you are correct. Limit will not increase, it may get overloaded. Correct. You were asking about this current assignment also. What your doubt?
Yeah, there is a similar question in the current assignment.
Yeah. That is multiple
Yeah,
choice.
yeah, yeah. What are the outcome of reactive power compensation?
Yes. You will get a similar type because that is the means like basic requirement that we are doing for this tutorial session.
This assignment question is different, sir. But it is outcome of power compensation.
Yes.
But what are the outcome of reactive power compensation?
Yes, outcomes means like advantage only.
But this is many
It is
reduction
opposite. It is opposite to this.
Yes,
But then
opposite this, right? Correct. It is opposite of this.
this is not a multiple answer. This is a single answer. MCQ
Yes.
only.
Got it, yeah, Shab. But this is the opposite of this. Here,
Yeah, that
in
is
the
very.
in this tick mark is the correct answer for the present assignment.
Yes, in that way you can also think. So let leave that problem. You just correlate with this problem for solving the question number 10. So concentrate on this second problem.
Can you put in a presentation mode, sir?
I am telling that concentrate on the second problem.
Can you put
You,
in presentation mode? Slide.
okay, okay.
Okay, thank you.
So what are the things we have provided? So we have provided with apparent power as 8000 kVA and power factor is given as 0.7. And the cost of synchronous capacitor is $15 per kVAR. Find the investment required to correct the power factor to unity power factor. So let us first find this power factor angle. Cos inverse of 0.7 is 5.573 degree. So sine phi is 0.714. So Q will be S into sine phi. So apparent power is 8000 kVA. Sine phi is 0.714. So it is 5713.143 kVAR. So whatever the reactive power demand of load that is supplied by the capacitor bank. And that is supplied by the synchronous capacitor. So you can also write QC equal to minus
Answer is
5000.
B. Answer is B, is it?
Yes, correct. Very good. 5713.143 kVA. Therefore, investment required so $15 per kVAR. Here we are getting 5713. So 15 into 5713.143. So 85,697.14 dollars. So B answer is correct. This is one of the very simple problem.
QC is the negative, huh? Negative
Yes,
value.
yes. Your answer is also correct. B is correct answer. For capacitor, your reactive power is of nature of leading reactive power, while for inductors, your reactive power is of lagging nature. Therefore, we consider for lagging reactive power positive and leading reactive power negative.
In this question, what is our target value is not mentioned, whether it is 0.9 or 0.8. Is it required?
What? I didn't get.
Target power factor is not mentioned. That is required.
What power factor is not given?
Target power factor. That means leading power factor 0.9.
No, it is
Compensation.
given. It is given as unity. Yeah.
Unity power factor is given. Na?
Yeah, unity is given unity.
Okay. Sorry, sir. I
Yeah.
did not.
Now, if it is unity, it is easy to calculate. You don't have to find the second
Yeah.
KVR.
Correct.
Directly you can take.
You don't need to also make this power factor angle. If you make, then it's also good. Means like if you consider power factor triangle, if you make this power factor triangle, then this is QL, and this is active power, and this is your apparent power. So all the power demand from the load, they are fulfilled by this QC. So Q and QC both get cancelled out, and finally this only how you can say this apparent power will becomes equal to active power after compensation. So this QC equal to magnitude of QC equal to Q. Magnitude of this Q equal to QC. You can say it like that. So it is given that unity power factor. That's why whatever the reactive power of load, that is being compensated by the capacitor. So now in this problem, they have told you to find this reactive power compensation, and that is not at unity power factor. That is, you have to improve the power factor, and you have to maintain the power factor at 0.95 lagging. Sorry, this is not about improvement. In this problem, you are asking that if the capacitor goes out of service, what will be the power factor of the industrial load? So let us make this power factor triangle. You can also use the expression that being sir has used in the class lectures. Whatever the convenient bit you are, you can follow that. It is not necessary that whatever the way I am using, that is the only way. You can use many other expression and many other uh, methods to solve the power factor correction problem. So with the capacitor bank, this power factor triangle we can find. Suppose this is without capacitor, so this is PL and this is QL. And let us consider this is the reactive power compensation by the capacitor bank. The net reactive power demand of the load is QL minus QC. You can also write this as QL dash. So the shunt capacitor is providing power of 2 MVAr. So this QC is given as 2 MVAr. So you can tell that QL dash equal to QL minus 2. and PL is given as 5 megawatt. So let us take the angle before combustion as phi 1, and after combustion we consider the angle as phi 2. So after compensation, this angle is cos inverse 0.95, and that comes out as 18.195 degree. So we know this angle. Now you put this tan of phi 2. Tan of phi 2 means tan of 18.195 degree. So it is QL minus 2 upon PL. PL is 5 megawatt. So tan of 18.195 is 0.3286. QL minus 2. Therefore, QL is coming as 2 plus 1.6434. So 3.6434 MVAR. Now you got this QL, reactive power demand of load before compensation. So you can easily find phi 1. Phi 1 is tan inverse QL upon PL. Tan inverse QL is 3.6434. PL is 5 megawatt. So it is 36.08 degree. And you have to find the power factor. Cos phi 1 is 0. Cos of 36.08, that comes out as 0.808 lagging. So B option is correct. Anyone got this answer? Yes. Any doubt in this problem?
This tan phi 2 is QL minus 2.
Yes. I have made this power triangle for power factor correction. So initially no combustion is happening. So QL and PL. And when reactive power compensation is happening through capacitor bank, through certain capacitor, then your reactive power demand of load is reduced. So it is QL minus 2 because reactive power compensation is given. With shunt capacitor operating 2 MVAR is given. So this angle reduced to phi 2. Now tan phi 2 you can write perpendicular upon base. Perpendicular is QL minus 2 and base is 5 megawatt. So you will get QL in MVAR. So 3.6434 MVAR. And now you got QL dash, that is QL minus 2. And you also got this actual reactive power demand for the load, means that reactive power coming from the feeder. So this phi 1 you can find tan inverse QL upon PL, that is 36.08 degree, and then you can find the power factor of the industrial load. that is 0.808 lagging. Clear?
That is indirectly we found these values.
What?
Directly we are founding.
Means like anyway you if you apply anyway this calculation is required. This much calculation you have to do. I think sir has provided one formula also, but I'm not using that formula because no need to remember. You use the perfect triangle, and it's easier to find through this perfect triangle, and your concept will also improve.
Yeah, this method is good. This method we cannot remember. Okay, thank you, sir.
Yeah. Yes, sir has given one expression in the slide number 9, where he has Q equal to T into tan theta original minus tan theta new. So whether you apply that way or you can approach this way also. Okay, let us move to the next problem. So here a load absorbs 100 watt active power and 70 VAR reactive power from a source of 250 volt 50 hertz single phase. Find the value of capacitor in microfarad to be placed across the load to improve the power factor to 0.9 lagging. So this problem we also solve using the power factor triangle with the help of power triangle. So let us write what are the things given. PL is given 100 watt and QL is given as 75 var, and it is single phase source 250 volt 50 hertz. And now you have to put the capacitor to improve the power factor to 0.9. So phi is given. So phi is given. Phi after power factor triangle after compensation. So cos inverse 0.9 is 25.842 degree. So PL is 100 watt. So this PL is 100 watt and QL is 75 watt. And now we are doing conversation. So QC we have to find, and the power factor angle is given after conversation. Let us write the reactive power demand after combustion is QL dash. So it is QL minus QC. So 75 minus QC. So this angle is given. This angle is 25.842 degree. So again you apply this tan expression, tan 25.842 degree. So it is QL minus 75 minus QC, and PL is 100 watt. .482 43 into 100, 75 minus QC. QC will come as 26.567778 bar. Here you don't confuse that here QC is coming positive because we have considered QC in this direction. That's why QC is coming positive. But reactive power, lagging reactive power being supplied by this capacitor, magnitude will be same. Understanding is important than this thing. Now we apply, we know that QC you can write reactive power is V square upon XC. If you have assumed this QC in the upward direction, then this QC will come as negative. QC is 26.56 and V square is given 250 square upon XC. So XC is 1 upon 100 pi C because 50 hertz is given. So C will come as 26.56 upon 250 square into 100 pi. So it is 1.3531 into 10 to the power minus 6 farad. So it is approximately 1.35 microfarad. C is the correct answer. 1.35 microfarad.
Sir, in case of 60 hertz, what is the value of XC?
XC is 1 upon 2 pi FC. 60 hertz it will be 120 pi C. Right, Ramesh?
Yes, sir.
So this is single phase, so no any problem. But if there is three phase, then you have to multiply with 3. QC equal to 3 into V phase square by XC. Since it is single phase, then no need to worry. But in three phase, total reactive power being supplied by capacitor bank is 3 into V phase square by XC. So let us see the next problem. So in this problem, this is theoretical type problem. Now I expect that answer from each and everyone. The problem that the analytical approach shows that the best location and size in view of power loss reduction for single capacitor bank for a distribution feeder with uniform load density is. And the options are at the 50% of feeder length and size of 0.66 per unit, at the 33.33% of feeder length and size of 0.33 per unit, and at the 66.66 of feeder length and size of 0.66 per unit, and at the end of feeder and size of 0.50 per unit. So you type your answer in chat box. Yes, I got one response. She is saying C. Another one. Yes, Dev, you are correct. C answer is correct at the 66% of feeder length and size of 0.66 per unit. So this is the thumb rule for capacitor placement. You can refer the last slide for this reactive power and compensation of distribution system with shunt capacitor. There it has been shown that the the optimal power loss reduction expression and what should be this capacitor size and the what should be the capacitor placement. So for lambda equal to 0, that means uniformly distributed load. So power loss reduction is 89% or 8 upon 9 per unit. Delta PLS is 8 upon 9 per unit for the capacitor. For the capacitor placed at x1 equal to 2 upon 3 per unit. Distance with 3 equal to 2 upon 3 per unit size. And this is well used two-third thumb rule for capacitor placement. So this is the well used, and we have in the initial during the starting of session we have solved the example where we have considered this capacitor location two-third per unit and capacitor size two-third per unit where we got this 89%. So from there also you can correlate. And this is the optimal location and optimal placement where we will get this power loss reduction of 89% when the capacitor is placed at two-third per unit and it is two-third per unit size. So you remember this point. This is very important because this is two-third thumb rule for capacitor placement. Now let us come to the problem 6. So a three-phase distribution feeder draws 320 ampere at power factor of 0.65 lagging, and it is supplied to a lump load. The ampacity limit of the conductor is 240 ampere. A capacitor bank is to set up at the load end to reduce the current to the ampacity limit, keeping the load current intact. The feeder length is 5 km. So without capacitor, it is drawing 320 ampere current and the current is flowing through the feeder. Now we have placed the capacitor bank to reduce the current to its ampacity limit. Now, with the help of capacitor, the current flowing through feeder is reduced from 320 ampere to 240 ampere. The feeder length is 5 kilometer. The feeder line parameters are resistance is 0.8 ohm per kilometer, reactance is 0.6 ohm per kilometer. Assume load in voltage as 11 kV. You have to determine the active power supplied by the feeder. Here you don't need to consider the compensation. Before the compensation, and also that this is active power, so there is nothing relation with compensation. Before compensation also and after compensation also, active power is not going to change. So here it is asking about the active power supplied by the feeder. So you find this, I am just coming in 1 minute. So yes, so what are the things given here? Load current is given. Load current IL is given as 320 ampere. And then load in voltage given as 11 kV. And power factor is given as 0.65 lagging. So with this only you can find the active power supplied by the feeder. PL is root 3 into VL into IL into cos phi. So root 3 VL is 11 kV. So 10 to the power 3. IL is 320. Cos phi is 0.65. So you will get 3962 3962.932 kilowatt. So this is the answer. So correct answer is A. 3962.93 kilowatt. How many of you got this answer? Yes, Yusuf, your answer is correct. 3962.93 kilowatt. Now let us see the seventh number problem. Determine the load demand in MVA. And options are 7.432, 5.906, 6.096, and 4.905. So it is also very simple.
Answer is C.
Yes, Yusuf, your answer is correct. C is correct. So you can find by two ways. You have already found this active power. So you can write SL equal to PL upon cos phi. So 3962 upon 3962.932 into 10 to power 3.65. So it is coming as 6096.818 kVA. So in MVA 6.096 MVA, or you can also directly apply SL equal to root 3 VL IL. So root 3 VL is 11 kV, IL is 320 ampere. So this is same 6.096 MVA. So C is correct. Yes, so your answer is correct. Now let us see next problem. Determine the power factor after capacitor placement. So you have to find the power factor after capacitor placement. So I am just drawing the scenario before capacitor and after capacitor placement. So before setting up capacitor, so we have substation and then feeder having impedance is given, and this is node or bus where this load is demanding power of PL plus JQL. So before setting up the capacitor, all the power is coming from the feeder PL plus JQL. Now let us find this impedance of feeder R plus JX. So R is 0.8 into 5 plus J 0.6 0.6 into 5, because resistance is given as 0.8 ohm per kilometer and reactance is given as 0.6 ohm per kilometer. And this line feeder length is given as 5 kilometers. So you have to multiply by 5 So 0.8 into 5 is 4 and 0.6 into 5 is 3. So this is the feeder impedance. And before the capacitor placement, all the power flowing to the load that comes from the feeder. And now you set the capacitor. Now after setting up capacitor, this reactive power flowing from the feeder is reduced. So BR reactive power is supplying QC amount of reactive power, and this load is taking PL plus JQL. So this impedance is 4 plus J3 ohm. So let us consider this is PL plus JQ feeder. JQ feeder is flowing from the feeder. So we know that after capacitor placement, this current amount is getting reduced. So you can find the amount of apparent power flowing through feeder, S feeder. Let me change the color. Those who are getting answer, you type on chat box, and you can solve by many ways. There is not a single way. So since we know that after capacitor placement, the current is flowing is 240 ampere. So S feeder is, so you can tell that I feeder that is flowing through after capacitor is 240 ampere, and before capacitor placement I feeder is I feeder is 320 ampere. That is the difference. That is difference. You can see what is the advantage of capacitor placement. After setting up capacitor, the current flowing through feeder gets reduced. Before that, it was 320 ampere. After capacitor placement, the current amount flowing through feeder is 240 ampere. So you can easily find apparent power flowing from the feeder is root 3 VL I feeder. So root 3 VL is 11 kV and I feeder is 240 ampere. So it will give you 4572.614 kVA. Is the amount of apparent power flowing through feeder. Now you can easily find the power factor of the feeder after capacitor placement. You can find it or not. Now you can find the So you can here also, because you know two quantities S feeder and P feeder, because PL is same. So you can find cos phi with the help of power triangle. But let me find this Q feeder first. Q feeder is S feeder square minus PL square, because PL you cannot disturb. All the active power from the come from the substation. So 4572.61 whole square minus PL we have found in the previous section, 3962.93 whole square. So this will give you 2281.22 kVAR. So you got Q feeder. Now you can find the power factor angle. So phi is nothing but cos inverse. Phi is tan inverse P upon Q. So P is 2021.22 and Q upon P. So Q is 280.22 and P is 3962.93. So we will get 29.926 degree. So power factor cos phi is 0.8667 lagging. So B answer is correct. So it is very simple. You just carefully read the question and solve systematically. You will get the answer. So here this power factor is given 0.65 in the initial. So you can easily remove one answer because this is less than 0.65, 0.59. So sorry, it is giving leading. It might be possible, but very rare case. But power factor less than this 0.65 lagging will be always incorrect after doing compensation. Now come to the next problem. Determine the capacitor bank rating. Now you have to find the QC. So you have to find the QC. QC we know that QL minus Q feeder. So QL we have found or not? QL we have not found. So QL we can easily find. So we know that initial cos phi is 0.65, and from here phi will come as 49.46 degree. So this will provide sin phi. So sin phi will come as 0.76. Therefore, this QL is root 3 into VL into IL into sin phi. So root 3 into VL is 11 kV. IL is before compensation is 320 ampere. Sin phi is 0.6. So QL will come as 4633.18 kVAR. Therefore, we can find QC QC is QL 4633.18. Q feeder is Q feeder we have already found 2281.22 kVAR. So it will give you 2351.96 kVAR. So it is closely matching with A option. So A option is correct. Still here any doubt?
Yes, sir.
Everything is fine.
Yeah, clear, sir. Great.
So you can approach any other way also, where you can just consider current only and this power factor. From that way you can also find. I have solved this type of problem in the previous assignment, in the previous session, last year's session. So you can go through it. But this is quite simpler way. So you just follow this way. For better understanding, you can refer the slides where I have solved just using the current. But that is quite lengthy.
Can we have the access to the previous question papers? No.
I've already provided here, like this for 2023.
Okay, okay.
You can go through the problems, because if you just look upon the problems, that will be helpful for your final exam, because very less chance that they will go beyond these so many problems. Because if you cover 2 or 3 years back assignment, all assignments, then I don't think that there is no question left.
And again, the questions will not be tougher than the assignments, is it? It will be easier than the assignment, is it? The exam?
No, sometimes uh, it may be tougher than assignment also, but in general case, they will ask similar to assignment problems, not easier than assignment and not tougher than assignment. It depends upon the faculty. It depends upon the course instructor. But in general case, they will ask similar to the assignment, because they have to consider every type of a student. So let us see the last problem, question number 10. So determine the magnitude of voltage drop of feeder after capacitor placement. So voltage drop magnitude. Is IZ. So it is asking about the capacitor placement. So after capacitor placement, what is the amount of current that is flowing through the feeder? Anyone can tell? After capacitor placement, what is the amount of current flowing through feeder?
240 ampere.
Yes, correct. So the current is reduced, so 240 ampere, and it is multiplied with R square plus root R square plus X square. So R square is 0.8 into 5. So 4 square plus 3 square. Reactance is 0.6. So 240 into 5. So it will give you 1200 volt. So this is all for the previous year assignment. Now you can also revise 2023 assignments where many problems are similar to this as usual the all assignments. So here they are asking about the reactive power supplied by each capacitor. So once you find the capacitance, means reactive power being supplied, then you can find reactive power supplied with capacitor by dividing it by 3, and you can find the capacitor value with the use of this expression.
The reactive power supplied by each phase will be similar, whether it is Y or delta.
No, it is not similar
The
because
reactive,
it is not similar. In if you connect in delta, it will be different. If you connect in star, it will be different. In delta, the voltage across this capacitor you see, this is line voltage coming,
yeah.
right? And if you consider this,
Y connection
consider
will be phase voltage.
yes, here this 3 into V phase square upon XC. So it gets changed. So reactive power being supplied by capacitor bank in delta and in a star will be different.
The total will be same, but each phase supplying will be different.
Yeah, means compensation amount is given. So in that way, total will be same, but each phase will be different. Right, correct. Because they will provide that your capacitor bank should provide this much amount of compensation.
Do you have an example for Y and delta separate calculations? No.
Yes. So I have, so after compensation, this is okay. So here you see this one.
Yeah, here the total is 132 kVAR.
So in this, it is a star connection. So uh, so this QC is 398.5168 kVAR, and each capacitor is supplying 132.83 kVAR. So this 132 kVAR is being supplied by each capacitor. So we have to deal with each capacitor here. So for each capacitor, the phase voltage coming across. So directly apply this expression QC equal to phase square upon XC.
Okay, we square by
First,
XC, fine.
yeah, and this QC is reactive power supplied by each capacitor.
From where this cube came, cube,
What?
the 11 by root 3 by cube, from where?
So 11 kV is line to line voltage. So load in voltage is 11 kV, right?
11 kV divided by root 3 is the phase voltage.
Yes, line to line
Then
is
why it is power of 3, not 2?
line to line voltage 11 kV. So V phase is 11 upon root 3. So this is this V phase
Yeah, this is okay. My question is, in this equation which you wrote, 11 divided by root 3 to the power of 3.
You wrote in a red mark, sir. 11 by root 3 raised
So it is
to
a square.
square.
It is a square, not
Okay.
Q. Sorry, it is square. So 11 by root 3 into square root 10 to the power 6, and that's way. And be careful, this is not total reactive power QC. Here, this is provided by each capacitor, right? If you write all, means like if you write total reactive power, then you have to apply this expression QC equal to 3 into V phase square upon XC, total reactive power. And then you have to put this reactive power 398. 398.516
398 is for the total.
total. And 3 into, you will get same answer. So be careful while applying expression. It is simple. Here, this reactive power is just supplied by each capacitor. So for each capacitor, Q is equal to V phase square by XC. Now you can go through this multiple select question where they are asking about consume leading reactive power. So these are theoretical problems you can easily solve.
I have a question. We have a doubt on this in multiple select questions.
Yes.
In multiple select questions, maybe if there is two answers, one of them was correct, you will not get half mark, or it will be completely should be correct.
No, for if you are, if suppose there are two means two options are correct, you are selecting one answer, then you will get half marks, right? But if you have selected one incorrect also, then you will not get any mark.
One correct and one incorrect means I will lose complete.
Complete, yes, right. Other one are simpler. Here, this type of problem is asked in the current assignment also. Here, where we have discussed in the initial, where this fixed capacitor bank is placed 2/3 of total active load and located at 2/3 of distance from the source. You have to find the total power loss reduction. Then you can use this expression that we discussed, 3 alpha C x1 upon into 2 minus x1 plus lambda x1 minus C into 100%. If you vary this reactive compensation and this placement of capacitor bank, then this power loss reduction will get changed. Just
This is
apply this expression.
confusing because of this long formula.
Yeah, little bit miss, but if you use more time, then it is very easy. So you replace this 1 upon lambda plus lambda square by alpha, 3
But
alpha C
when it
x1.
is uniformly distributed, there is a clause lambda is equal to 0 is, yeah.
Yes, yes. And this one. And for 2022, almost all problems are similar. So here also we have considered both delta and star. So like for delta, this QC is coming as 3 into VL square upon XC. And for a star, total reactive power being supplied to capacitor bank is 3 into V phase square upon XC. So this capacitor size will vary. So you can see this for delta, this capacitor size is 1/3 of the capacitor size in a star. In a star only, capacitor size is bigger than delta for the same reactive power compensation. See, for
Yeah,
delta, we have
because of the
this.
voltage, because of the voltage change.
Yes, correct. For the delta, for the reactive power compensation of 168 kVAr, we have this capacitor value of 8.6 microfarad in delta, while for this star connection, we have this capacitor value of 25.8 microfarad. Okay, I hope you will be able to solve the problems for the current assignment. Any other thing you want to ask?
I think, sir, this will upload in our portal.
Yes, it will uploaded today. after half an hour.
Okay, nice.
Okay, then.
Thank you, sir.
Welcome. If there
Thank you,
is no
sir.
doubt,
Nothing, sir. Nothing from my side. Thank you.
okay. So we will meet on the next session. Thank you for joining the session. Good night.
Yes, sir.
Thank you,
Good
sir.
night.
Sir.
Good night. Thank you, sir.
Welcome.